Hi. Today I want to talk about changing variables in the 2D world when we do integrals, usually called a u-substitution. I like to think of these sometimes as chain rule in reverse, the chain rule for multiplication, but backwards. And I'm going to start with these two integrals because I think they're pretty easy to do, but I'm not sure that I've given them careful thought, like how they compare. So let's take a look at them. So this first one here, let's do an antiderivative. The antiderivative of sine would be negative cosine of x. And we're going to evaluate that from 0 to pi over 2. So we'll get negative cosine pi over 2 minus negative cosine 0, which ends up being negative 0 plus 1, or just 1. And geometrically, what you've done, you sort of know, right? Sine x looks like this. It goes up and down like that. And we found the area until we get to just pi over 2. And what you found is sort of like the area of this little wedge. Okay, let's take a look at this other problem. This other problem here is sort of a classic for a u-substitution. Some of you probably wouldn't even use a u-substitution in this case, but let's do it anyway. Let's just force it. So I'm going to let u be 2x, because that's the thing that's inside. That's the function within a function. Maybe you do du dx equals 2. So that tells us that dx equals du over 2. And so that can get subbed in here. You can get subbed in here. We can change our limits of integration later. We'll deal with that in a minute. So this becomes the integral. We'll leave an indefinite integral for now. This will be sine u du over 2, which I can rewrite as 1/2 the integral of sine u du, which becomes negative 1/2 cosine u, uh, technically plus a constant. We're just going to plug back in u though right away. Remember, u is 2x. That was the substitution that started this whole thing. So we're getting negative 1/2 cosine of 2x, and then that's going to get evaluated from 0. And in this case, we went to, if you look at that upper bound there, it's pi over 4. So that's what's going to happen here. This upper bound is pi over 4. If I plug things in, I get negative 1/2 cosine of 2x times pi over 4 minus negative 1/2 cosine of 2 times 0. This thing here, this becomes negative 1/2 the cosine of pi over 2. And this becomes plus 1/2 the cosine of 0. Now this should be pretty familiar. If you look at this term here, and you go up over here, hey, that's the same thing. The difference is this had a coefficient of -1, and this is a coefficient of -1/2. And cosine 0 is just 1. So when you're finished here, you end up with -1/2 times 0 plus 1/2 times 1, or just 1/2. And if you think about it, the picture looks very similar to the picture we drew for the other integral, which I kind of tucked up here, but here it is. I'll circle it. There's the picture for the other integral when we went for sine x from 0 to pi over 2. This integral is we're graphing y equals sine of 2x. So if you remember correctly what sine of 2x does, this means that your frequency, this is sometimes called the frequency of the trig function, which means we'd have two complete sine curves from 0 to 2 pi. So on the graph, what ends up happening is the graph gets squished horizontally a little bit. So what will happen is well, normal sine might do this, and this is pi, and this is pi over 2. This function up here, y equals sine 2x, ends up get everything done in sort of half the distance. That's a terrible picture, but you'll just have to forgive me for it. So this red curve is the sine of 2x. But in our new integral, we graphed y equals sine 2x, so we had this horizontally compressed figure. It was done by the time it got to pi. but we only found the area up to pi over 4. And sure enough, when you look at this wedge, this green wedge we've got, that looks just like this green wedge up here. It's sort of like the same picture, except this base had this wedge had a base of length, like this distance horizontally here. Let's use a different color now. That yellow distance was pi over 2 units of length, and this yellow distance is pi over 4 units of length, which you'll notice is exactly half of the previous length. And your area of this green wedge was 1/2, whereas in the earlier problem, it was 1. So changing variables to compute the value of an integral amounts to a dilation, or in this case, just a dilation of the region. We squished the region's length by 1/2. And so, but there's other things we can do. The dilations belong to a class of objects called transformations. So what you're doing really is you're taking your integral, you're transforming the region into something else. And as a result, you get the scale factor of 1/2 here. Is what happened. Now, where is that 1/2? That 1/2 is actually hiding in the integral, but I'll show you. There it is right there. I'm circling in blue and put stars next to it, and that came out in front. And so this change of variables amounted to multiplying our old area by 1/2 because we've squished it horizontally. Okay, so what I was hoping to do here was give you a sense of not only review how to do a u-substitution, a very basic one, but give you a sense of what a u-substitution actually does geometrically. It's going to set us nicely for the next video where we move into something called the Jacobian. And the Jacobian is a special matrix that can help us change variables when we're doing either double or triple integrals. Thanks for watching.